In this video, we're going to calculate the loads for the fuselage of this aircraft. That will be needed to design and finalize its structure. So here we see a final detailed design. Now, the structural layout of this aircraft includes an aluminum inner structure that accumulates loads and transports them throughout. And it also has a wooden outer structure that bridges local loads from the outer surface of the aircraft towards the closest inner structure. And it also supports lighter masses. It has mounts for them such as passengers. These are the tennis balls from the 2017 regular class rules. And batteries, we have the ESC, servos, hinges, things like that. And in addition to the wooden outer structure, we also have plastic 3D printed tips at the wing tips and the nose here. Now, at this stage of the loads calculation and the inner structural optimization, we wouldn't have to be finished with all these detailed wood and plastic parts. What you might have at this stage is an initial design of the internal metal structure, as well as a layout of where the passengers and the cargo and the systems will be positioned. We'd have an initial estimate of the performance and maneuvers, and the wing and stabilizer and propulsion performance, everything we need to move that mass around. Now, if our internal structure layout is dependent on the external surface, like it is here with these wings, because the wing box is as close as it can be to the outer surface of the aircraft, so this structure, the inner structure here, depends on the outer surface. So if you have structure like that, then you'd have closer to finalized outer surfacing of the aircraft. And we also wouldn't necessarily have the landing gear finalized. What you really need at this stage would just be where the wheels are, the positioning of them, and how the landing gear attaches and where it attaches to the fuselage or the wings. So in this case here and under here and over here. And other than that, at this stage, you would just really need to know for what's in between those two ends, you'd mainly need to know the mass properties and the suspension properties of the landing gear. So at this stage of the initial loads calculations, you wouldn't need an aircraft that looks as finalized as this. We're going to use the loads and go through some loops of load, stress, and design to finalize the structure before doing all these details. It is true that in SolidWorks you could reference the final level of detail in the wood structure to the metal structure and the outer surfacing, so that when you update the metal and the outer surfacing, the wood at the outer parts updates as well. So designers could go ahead and start filling in the details knowing that the inner structure might change. But keep in mind that at the final level of detail, there tends to be a lot in the model that breaks if you update a couple of levels above. So the designers can move ahead, but they have to keep it in mind that the inner structures definitely will be updating. As far as the mass properties of the wood portions of the structure, we would go with an initial guess based on past designs, thinking about how many frames and ribs there will be per length and how much they weigh. Now, other than its mass, the wood does not contribute parallel to the metal structure in a way that transports loads throughout the aircraft. It only or almost entirely transports loads from the surface and supported masses to the metal structure locally, so that would be like in series with it. Now you might be thinking that, hey, if this wing is in bending and we have this internal wing box here, the aluminum structure, why aren't these stringers that are all the way on the outer surface of the wing also helping it in bending? There's a good reason why they aren't doing that, at least hardly at all, and their role is almost entirely just to bridge the local loads, the local air pressure, and move it from the skin around them into the stringer, into the ribs, and move that down to the closest internal metal structure and not contribute to the overall second moment of area, like what resists the bending of this wing. So more on that later, but for now we're just going to hide all the wood and just visualize the metal internal structure, and we're just going to imagine that we do have some design in the future of this wood that will move the external loads towards into the internal structure. And so we're going to hide all that wood structure, and the loads that we calculate are going to be all about sizing the internal metal structure and assessing its strengths. So here's where we're at this stage. We have the internal structure, the systems, and the payload. So we know the weight of each of these structural components. We'll first take a guess of maybe with just some hand calculations, just a guess of, for instance, the thickness of the skin. They're transparent in this view. The thickness of the skin of the wing box, maybe the thickness of the walls of the keel beam, that type of thing. We'll just guess for the first iteration. And we don't have the fasteners in here yet. We would just guess an added weight for how much those will weigh. So we know the initial weight of each of these components, and we know their position. What I've done in this design is I've designed the origin to be the CG. So as I'm putting in, you can click on the origin. As I'm putting in any components, for instance, the passengers and the payload in this that goes inside this beam underneath, as those are going in, those will be designed so that their CG is at the CG, at the origin. And as you're putting in the rest of the components, you can keep track. You can try to get the CG to stay at near the origin. And if anything is off near the end of the design, we can always move, for instance, the battery can move forwards to adjust where that CG is to get it in our intended location. So the calculations we're going to do in Excel, and we're going to start by inputting the masses and their distribution throughout the aircraft into that spreadsheet. So this is the final output of the loads calculations for the fuselage that we'll be doing here. So it's the shear and the bending moment within the structure of the fuselage that it'll have to be designed to resist. We're starting with the mass property sheets. We have 3 here. And you can follow along. You can download this sheet in a link below. But chances are it's not going to work for your aircraft, your specific aircraft. But you can take things you learn from this sheet and this video tutorial to create your own. Now I've got here black cells as calculations, and anything blue is an input. So here's just a list of components, and I've put in the vertical tail as just a component sort of attached to the fuselage, since it's not producing any aerodynamic forces up or down. And so here's the rest of for instance, the landing gear, nose gear, servos, ESC, battery, things like that. So those are components. It's not entirely done. It's just sort of an example sheet. You'd probably have a longer list. Now, since this is the fuselage, we're using fuselage station as a reference dimension, which is in inches here. Now, whereas in the design, in SolidWorks, I use the origin as the target CG. Here, I'm using the front of the propeller as 0 fuselage station. That's because the actual CG that we calculate here is not necessarily at the target location. So we're calculating here, and also it's easier to deal with this dimension if it's always positive. Now we're approximating the mass distribution of each component as evenly distributed along its length, each of their lengths. So we can imagine each of these components as a simplified, sort of like a rod or a plate oriented along the fuselage length. And in that case, then, to fully define each of them, we just need their weight, the fuse station of where their CG is, which is the middle of the components, and the length of each of the components. And that completely defines the mass properties for each of the components. So we're in imperial, and we'd rather use inches than feet. So here, for mass, we're using slugettes, which is 12 slugs. It sounds a bit weird at first, but it works well if you use gravity in inches, then you can use slugettes with, over here there's a conversion chart for it. So we have the fuselage mass properties. Now we're also doing the wings and the HStab. Those are defined by just these 4 numbers here, the root chord length, the weight of the wings, the CG percent root chord, which would be, so if the CG is at 30% chord, then the CG is along the length of the chord, it's 38% of that. And this is the fuse station of where the CG is of the wing when it's attached to the fuselage. Now, in order to keep using this approximation of these masses as just single rods that are evenly distributed, so their CG percent, each of these components has a CG percent of 50%, right in the middle. I've made this approximation of the wing as just sort of 2 of these rods, with their length and mass adjusted so that the CG of the 2 of them is at the CG percent root chord of the wing. So that makes it so that these 4 numbers of your wing can calculate all the rest of this, which is the forward and aft segments of this sort of approximated mass distribution for the wing. And that's the same thing we're doing for the HStab here with these 4 numbers. Now notice that in all of these we are calculating the moment of inertia, the moment of inertia about the y-axis, which is pitching. So that's because we're doing the fuselage, and as we come in to land, we're going to be pitched up like this, and we're going to hit the ground at the wheel, which is behind the CG in this tricycle configuration of aircraft. So when we hit the ground, there is a torque, sort of a pitching moment forwards. So there's going to be an angular acceleration on the aircraft. So in addition to knowing the masses, we need to know the moment of inertia, the mass moment of inertia about the, well, in SolidWorks it's the x-axis here. So we accumulate all of this information from the past 3 tabs into this final tab where everything here is calculated. And this is all the mass properties that we need to know. So here we can calculate the total mass of the aircraft, the CG location, both in terms of fuselage station and also in terms of percent root chord. This is the CG of the whole aircraft, located in terms of how far along the chord of the wing. Now that's a useful measure for, this is mainly for the aerodynamics people, but in terms of just calculating the loads, we just need this number here where the CG is. So in addition to calculating the total weight, we also calculate the total moment of inertia of the entire aircraft about the pitch up and down axis. Now in terms of that calculation, for each of these components, we have its mass, we have its length, and the IY of an individual component, because we're estimating it as evenly distributed mass in the shape of a rod or a plate, that IY about the CG of the actual component itself is just 1/12 times the mass of that component times the length of it squared. And as far as the contribution of the component about the CG of the aircraft, we're also adding in, due to the parallel axis theorem, the mass of the component times the distance of that component CG from the aircraft overall CG squared. And so we have to add up each of these individual components IYs plus the parallel axis theorem IYs. Now for the landing gear layout tab, we already input its mass properties, so we have the main gear and the nose wheel here. So the information that's lacking that we need to input is just where the main wheels contact the ground in terms of the fuse station, and where the landing gear attaches to the fuselage. Here I put them in the same spot, sort of like as if the main gear was vertically attached. So now we need to know about where the lift is applied along the wing chord, or at what fuselage station the wing lift is centered at. So we need here this input table. Now that's coming from the Aero people designing the wing. All we need to know for loads is, if the wing is giving a certain lift, what is the center of pressure chord fraction where that lift is applied along the wing. So all of this is only valid for a certain speed or Reynolds number. So you could also get a 3D table for various speeds, but we're focusing on that one speed that we land at here. So all we're needing is this table here, which is if your wing lifts a certain amount, where is the center of pressure located along the wing? And that's because as the aircraft changes angle of attack to adjust for how much lift it needs from the wings, the center of pressure of where the lift is applied along the wings actually moves forwards or aft quite a bit for these cambered airfoils that are often used on wings of SAE Aero and design build fly aircraft. Now for the HStab, because it's much less cambered and it's not producing nearly as much lift, we're going to assume that it just stays at the center of pressure stays at the quarter chord, the 25% chord. If you need a refresher on this, you can check out the video on airfoil coefficient of moment. And then knowing that, you can understand the wing coefficient of moment much easier. Now, before we check out the calculations that are going on in this Aero sheet, we have to look at the dynamic sheet because they're coupled. So in the dynamic sheet, we have a free body diagram of the aircraft that is coming in and landing. So the maneuver that we're looking at here is a landing where the aircraft is approaching in a flare that is just above 1 Gs. So here I put 1.1 Gs for the aircraft flare. That's the aircraft that's coming in, and just before it touches the ground, how much Gs is the aircraft experiencing at its CG, and well, actually at its entire length, because we're assuming that it's not doing an angular acceleration before it touches the main gear on the ground. So the lift of the wing needs to account for, and the downforce at the HStab and the weight, that's all balanced for this 1.1 G approach before it hits. Right after it hits, the lift on the wing is still the same, right as the ground hits the wheels, but we have an upwards acceleration of more than 1.1 Gs, and we have an angular acceleration because the wheels are behind the CG in this tricycle landing gear configuration. So here I've put a landing load factor of 4. So the aircraft is coming in doing 1.1 Gs, and then the main gear hits the ground, and the whole aircraft experiences an upward acceleration of, actually, because of the angular acceleration, I'm defining this 4G load factor to be at the CG. You can estimate what a conservative load factor is for your aircraft from videos of similar aircraft landing, for instance, from competition videos. And you want to put in a typical hard landing that you'd want the aircraft to survive, but not necessarily over-design for what would essentially be a crash. So if you have a suspension landing gear, you can put a lower load factor here. And the actual load factor that you put in can come from performance estimations. A good reference for that is a book called Aircraft Performance and Design by John D. Anderson. Now here we're calculating the wings lift and the HStab downwards lift for the in-air flare just before touchdown, which is, we're assuming these two are still applying just after the touchdown, when the wheels force are happening. Now, even at 1G, we actually need more wing lift than the weight of the aircraft, since the HStab needs to push down to balance the fact that the wing lift is behind the CG. For more info on why that is most often the case, you can check out my series on stability. Now, as we saw in the previous sheet, the location of the lift, and thus the resulting HStab force required, is a function of the lift value itself. So this is an iterative calculation. So here we use a goal seek to balance out this cell, which is the wings lift that we achieve from a given angle of attack, minus the wings lift at the dynamics calculation, which is a result of trimming the aircraft given a certain given this load factor and given a trimmed aircraft so that there's no angular acceleration before it touches the ground. So essentially the HStab and the wing lift and the weight of the aircraft are balancing out their torques. So here the iterative calculation came up with, you can see this is 39.7 COP percent chord. So that is coming from here, this table. So 39.7 is about here. So the aircraft at that 1.1 Gs is saying that the wing is at an angle of attack of about 4.1 degrees, let's say. So the wing is at 4.1 degrees, so that means, just for reference, if your angle of incidence of the wings is, let's say, 3 degrees, then that means the overall aircraft is at an angle of attack of like 4.1 minus 3, which is like 1.1. Because that's what you can adjust, the HStab can adjust the overall angle of attack of the whole aircraft. We can't change the angle of incidence of the wings. So that's what's going on here, is that this is in gray because it's just reference. What's important for the calculation is just at, let's say, 4 degrees, you have 62 pounds of lift, and the COP percent chord is at this 39%. So we can give an example, like let's say we were changing this to 1.5 at the approach. So here, if we're just putting in here, we could put in a bunch of numbers we want. Let's say here we can see that we are lifting 62 pounds at this 39% chord center of pressure, but we need 84 pounds. So we could go in here and say, okay, what if we're actually at 35, and that moved it up to here at 81 pounds. So we're getting closer to this number here. And actually the 84 reduced because as we moved that center of pressure, the HStab lift changed. So that was actually a very close guess, because this number is now close to 0. So we're just changing this number up here until this here goes to 0. And I've made this button here that can move this around and recalculate this dynamic sheet until the difference between the lift that you're getting from this table and the lift that you're acquiring from the free body are the same. So the difference is 0. So if we go back here and put, like, let's just say we're going to do 1G, which is just a in-cruise flight, we can go back, and now we're providing too much lift, 77 pounds. The dynamics is only asking for 55 pounds. So if we press this, that's just gonna, all it's gonna do is vary this number. So we'll let it do its thing. There we go. So it varied it until we got to an angle of attack that works, so that here we're requiring 57 pounds and we're giving 57 pounds. So the difference between the two is almost nothing. And so that means that at this 1G cruise, so we have 41% chord here. That would be over here. So we have an angle of attack of about 3 degrees. And well, you can tell from the design of this aircraft, I mean, the angle of incidence was 3 degrees, so the angle of attack of the aircraft as a whole is almost 0 here. So we're at a pretty efficient configuration in cruise. But that's not what we're doing right before landing. We're doing a flare, so I'll put it back to 1.1 Gs. That instant before landing, we're pulling a little bit more Gs. And here we don't have enough lift here. We're lacking 5 pounds, 6 pounds to get that amount that we need. I remember this is saying 62.97, but as we move the center of pressure while changing the wing, that HStab is going to require a different amount because of the torques balancing each other. So we'll let it do its thing. So it moved to 62.2 pounds now. So a bit different. And that's a balanced, this is balanced now at 1.1 Gs. And that's balanced these two are balanced with the weight of the aircraft for that 1.1 Gs as it's coming in. And then right as it hits, maybe from the videos that we've watched for our landing, we can estimate, like, because of the sink rate and all that, the sink rate and how much time the aircraft takes to transition from its sink rate to not sinking anymore once it touches the runway. Then we can estimate, like, let's say 4 Gs here for if we have some relatively thick tires. If we have very thin, like plastic tires, maybe we'd have to do more. Maybe we'd have to do 6 Gs. If we had suspension, like very plush landing gear, maybe we could even put 3 Gs, something like that. But for the example, that's what I've got here. So that's what these two tabs are doing together. And so we see that along with this overall acceleration, the N of 4, we also have that alpha, that angular acceleration, the pitch down acceleration. And what that does is we're mapping out here the acceleration along the fuse station. So at the front of the aircraft, the nose, we only have 2 Gs. Whereas all the way at the back, the 86 inches of fuse station, we have 6 Gs. So, and we defined it so that at the CG of the aircraft, which is here, it's at 41.5 almost. There, it's 4 Gs. So what's happening here is kind of like when you're sitting at the very back of a school bus and you go over a bump. The back of the school bus has more acceleration than somewhere between the school bus wheels. It's kind of a similar situation. But if you want to simplify your analysis, something you could do that's not that wouldn't change too much in terms of the actual load numbers themselves would be to say, okay, we're going to estimate that the reaction of the landing gear goes directly through the CG. So, I mean, when you look at the aircraft from the side, I mean, this one, if the CG is somewhere in the wing box there, I mean, you'd have to be pitching quite high for the reaction to go right through it. That's about where the CG is. If we look at the origin, then, I mean, we'd have to be pitching like that for the reaction to go right through the origin. And in reality, we're probably pitching something like this. But, I mean, it's not going to change that much on your analysis for how much it simplifies it if you want to do that as a first go of the loads calculations. But for the rest of this sheet, we are taking into account this angular acceleration when we're touching down. And yeah, you can go through the free bodies here. So we did these calculations as a whole aircraft, but if we're going to do a free body of just the fuselage, then we need to sort of take the wings off and take the HStab off and look at what forces are moving from the HStab to the fuse and from the wings to the fuse. And that's this tab here. So this sheet, the wing reactions, we've just looking at just the wing itself and looking at the connection between the wing and the fuselage is at the spars or the wing box. So the inputs here are in blue again, and there's sort of two different ways that a structure could move the resulting force and moment that it's putting from the wing structure into the fuse structure. And well, as far as that force and moment itself, that's a result of both the inertial forces of the wing and the lift, that is the lift and the torque due to the lift coming in through the wing box or through the spars about that structure's elastic axis. So the two ways that it could happen would be that if we want to look at two extremes, if we look at the structure here, the HStab is one extreme where these are the two spars, and if the lift of the HStab is right in the middle between those two spars, then we can tell that each spar will have an equal reaction. And if the lift of the HStab is in front of the forward spar, then we're going to have one spar reacts a lot in one direction and the other spar reacts a bit in the opposite direction to balance that torque. So the resulting lift and torque in this case is entirely done by the just two passages of shear from one spar to the fuse and the other spar to the fuse. And each individual spar does not pass any moment, but the resulting two shears passed to it equate to the moment and force that the HStab is putting on to the fuselage. And the other way that it could be transferred is, let's say in this case with this wing box, here we have the spars, the front and aft spars can transfer a shear, like an upwards or downwards force, each of them. But also there's horizontal forces that can be transferred from the skins. There's shears in the plane of the top skin and the bottom skin, and the overall wing box can transfer a torsion from the wing. Here we have the structure of the wing, and it attaches to the structure of the fuselage, and it can, in this case, maybe some of if the lift of the wing is ahead of this wing box, then we would have like a pitching up torsion transferred into the fuselage, and that could be done by a difference in the shears at the spars, but also by a torsion directly through the wing box. And I've sort of accounted for both in the sheet. You can put in sort of a percentage of how the torsion is transferred from the wing box or spars to the fuselage. Here for the wing, I put sort of half and half. There's half that torque is transferred through the torsion of the wing box. Half is transferred as a difference in the spar shears that are from one to the other, and that's going to depend on for your layout. That's going to depend on relative stiffnesses. For instance, if the top and bottom skin are very thin, then maybe, and if the spars are thicker, then maybe this percentage will be higher. And really, it's a guess here. But at least for the HStab, this is the same sheet for the HStab. At least it's very clear there that it's 100% because of the moment is transferred due to the difference in shears of the vertical spars. And 0 is from the horizontal skin, because if we look at the HStab, there is no horizontal skin, and even the way that these spars are attached about themselves, they cannot transfer moment to the each individual spar cannot transfer any moment to the fuselage, because here they're mounted on like a spherical bearing. So yeah, that's what I've done in these two sheets. And once we know so we've taken off the wing and the HStab, now we can calculate the actual external loads that are put onto the fuselage. And it's kind of confusing when we say external loads, even though if if we look here at this, if we look at the, let's say the keel beam, it has a mass and it's accelerating upwards. So its inertial loads are being applied to it. And we can imagine the forces are being applied inside the metal where that weight is. But in terms of the terminology that we're talking about here, external loads means applied loads. So the inertial loads, even though they're coming from within the structure itself, we're going to call them external loads. They're applied onto the metal. Whereas the internal loads, the shear and moment that we're going to calculate, those are the accumulated loads within the structure that it has to resist to keep itself together. So here we have, we've broken up the fuselage into 10,000 segments, and each of those is 86 over 10 thousandths of an inch, so that at the end we have 86 inches long. And we know the acceleration in terms of inches per second squared at every single one of those fuselage stations from the dynamics tab. And so that's the acceleration in inches per second squared. This is in G's just for reference. And this is the masses of the fuselage from back in the mass properties. Now, at each of those segments of the fuselage, these masses are giving their inertial loads, and those inertial loads are being accumulated into the fuselage structure. So, for instance, the propeller, it does exist between 0 and whatever half an inch, and so it is contributing here to some downwards force. And if we scale over, like this, for instance, this is at 5 inches of fuselage. Here we have two components here that are contributing. They are the limiter and the keel beam. So that's what all of these are. These are the distributed forces of the here we can link these. These are distributed forces in pounds per inch of each of these components. Now we also have point loads, which is in terms of shear, it's from the wing forward spar and the aft spar. Those are calculated at the wing reactions and just flipped in sign. We have it from the landing gear where it attaches to the fuse, and we have from the HStab. And we're also inputting direct moments, in this case just from the wing box, because that's the only structure attached to the fuselage that can directly torque onto it as an applied moment instead of as two different applied shears here. That would be like on your VMT diagrams. Here you would have an applied moment, although it's a distributed one between the wing box start and the wing box end fuse stations. So here it's a graph of the acceleration. So this column, and here this is just the sum of the distributed forces. So this is just we can see sort of, so this is where the payload is. So clearly we're getting a lot of forces there, and the point forces here. We have the two wing spar reactions, the landing gear. We have the two HStab reactions back there, and this is just for reference. We have where the CG is. So now we have all the information we need to accumulate all of these external loads and applied loads and moments to the structure overall to get this graph. So what that looks like is we have, again, we have the 10,000 increments and the x along that, and the shear. We're going to accumulate the shear as from distributed and from point loads, and accumulate the moment as well. Now, to do that, we can take a look at this sort of free body of the fuselage and the applied loads. Now we can imagine these are the applied loads, like this is a general situation. This distributed load and these point loads, the reactions here are the f of x, and if we were to look in, sample at any point along the structure, then we know that the resultant, the forces within the structure, this V and M, have to make sense if we're looking at either side. So if we do a free body where we slice it here, then we can, I mean, physically you can clearly see that the shear is a function of just the integral from, so the shear at this chi is the integral of the forces, including this point force and all this distributed force. It's the sum of it, it's the integral of it along this whole length. So that this situation balances. Now the moment, for me, I most clearly see, in terms of a physical understanding, the moment as this integral here, which is the moment must be an integral from 0 to chi of the forces times chi negative x, because these forces are contributing more and then these forces less to that reaction. So this is more clearly, to me, that's the physical interpretation of the moment. And we could do that in the calculation in this sheet, but it's more practical to, I mean, in most textbooks, you're going to see the moment to calculate it is just this integral from 0 to chi of the shear itself that we had just calculated, this V. And to me, it's not physically obvious why that is. And I mean, in some textbooks, you're going to see a physical derivation of why that is. But to me, I'd rather see the physical derivation in terms of this integral. And then you can trust here that this is equivalent to this because of the math in between, which is integration by parts. So you can take a look at this, and that's how I convince myself that the moment is just the integral of the shear. So if we take a look back here, we're going to get the shear from the distributed loads, which is this here, and we have to add the point loads. The point loads from to the left of the x that we're at, and then the moment from just the shear itself, which is just an integral. I did a trapezoidal approximation, and we also add the distributed moment, so that's 0 everywhere except where the in this case except where the wing box is. So we'd have to go find where the wing box is, which I think is at like 40 something inches. And there, here we go, we see the distributed moment coming in at the wing box. And yeah, then we just calculate the moment from the shear plus the distributed moments, and come up with this here, which is the output of this video, which is, this is the shear and bending moment within the fuselage structure due to that maneuver of the 1.1G flare into 4G touchdown of the main gear. You might notice here that, if we look at here, we see it in the general free body of a part that we're going to do a loads diagram for. We generally have these reactions that we haven't calculated for. And in our case, we didn't have any of these reactions because our case is, it's not a supported beam. It's actually an aircraft in the air, or we can sort of imagine the main gear as a support, because in that case, that's kind of like a reaction. But in these that you'll see a lot in the examples of the earlier free body diagrams that you're going to do the loads diagrams you're going to do. These cases are non-accelerating systems, so you just have sum of F equals 0. Whereas for the plane that we just did, we have an accelerating system, and in its frame of reference, then we have sum of F minus MA equals 0, and sum of torque minus I alpha equals 0. So we didn't really calculate for the reactions, especially, if we do a maneuver in the air, then we're not calculating any reactions on the aircraft, because it is an accelerating system that's not supported by anything except for itself. So that's one point to look at. As far as assumptions that we made in that analysis, so we did include the suspension properties of the landing gear. So that goes into the calculation of what the load factor is. But we assume the rest of the aircraft is completely rigid and stiff. So in reality, if we hit the ground at 4 Gs, the wings far from that attachment point are going to flex downwards, or have an influence to flex downwards, and the fuselage far from that attachment point is going to flex downwards as well, and that sort of provides like an alleviating load factor on the extremities. But overall, I think that would reduce the wheels force as well. So as long as the assumptions we make are conservative, then as long as they're not way too conservative, then we can keep them like that. So what do we do with the output here of the loads? Well, downstream is stress calculations. So we would take the loads we calculated, the M and V, and apply them to regions or cross sections of our structure, and check how overbuilt it is or how underbuilt it is, and how much we need to beef it up to resist those loads to be just strong enough and not too heavy. But before we did that, so this output here is a balanced load diagram. It's sort of it's the view of sum of F minus MA equals 0 and sum of torques minus I alpha equals 0. So this balances for that one maneuver of the 1.1G flare to 4G impact of the main gear. So that would be called a 2-point landing. But we have to check a list of maneuvers that each one of them might be critical for our structure at different areas. So, actual aircraft programs these days have hundreds of these maneuvers considered that each are potentially critical. For instance, you'd have maybe a side slip at such and such speed and altitude, and another side slip at another speed and altitude, and those might be critical for various areas of like maybe where the the V-fin attaches to the fuselage, that type of thing. And each of those maneuvers will be balanced. So for the fuselage, we might have like a 2-point landing, a 3-point landing, and in a 3-point landing, the nose gear would be involved. So you might have more of a moment right behind the nose gear. And we would also have maybe even just a pull up, like a 2.5G pull up or a gust, that type of thing. So for instance, in this sheet for if we wanted to do a symmetric maneuver, let's say we're doing, this sheet is entirely designed around a 2-point landing, just a main gear. But if we were doing just a pull up, let's say we could do, let's say a 2.5G pull up. We could put 2.5 there and also 2.5 here. And then we would be sure that the wheels are not getting involved at all, but the aircraft is pulling that maneuver. And we could look back here and see what the loads diagram looks like. So each of those individual ones, we'd have an output for these loads diagrams. And as far as what we design the structure to, we have to make it strong enough for any one of those maneuvers to be happening to it. So we would build up a final output for the fuselage that would be called an envelope loads diagram, which would be the maximum, at every single point, it would be the maximum M and the maximum V of both signs that could be put on the aircraft by any maneuver. And that overall M and V diagram, clearly it won't be balanced at the end, but that's just a reference as we check the structure for at any point here along here, what's the max M and V that could occur. And often they're labeled for, if there's points along it, you might label them for what maneuver produces that maximum moment. Like for instance, here it might be because of the 1.1G flare to 2G 2-point landing, and maybe a 3-point landing would be less here. So you'd label this as the 2-point landing, and then here the moment for a 3-point landing might be more. So here would be labeled with the 3-point landing. And even further than that, so that envelope would be just for the fuselage itself, and you'd also have loads diagrams for the wings, HStab, and vertical stabilizer. And you would also have, so this is the vertical shear and the moment in the pitch up and down directions. You would also have loads for the side-to-side direction. Thanks for watching. That was the loads calculations for the fuselage of this aircraft. Stay tuned for some qualitative videos on understanding load paths, on buckling, and of course more design videos.